Chapter 5: Gases and the Kinetic Molecular Theory. In this chapter, we'll first have an overview of the physical states of matter, and then we'll discuss gas pressures and its measurement, the gas laws and their experimental foundations, rearrangements of the ideal gas law, the kinetic molecular theory, and finally, we'll discuss real gases, deviations from ideal behavior. Most substances can exist as a gas, a liquid, and a solid under appropriate conditions of pressure and temperature. A gas adopts the container shape and fills it because its particles are far apart and move randomly. A liquid adopts the container shape to the extent of its volume because its particles stay close together but are free to move around each other. A solid has a fixed shape regardless of container shape because its particles are close together and held rigidly in place. Compared with liquids and solids, gases has many unique properties. Gas volumes change significantly with pressure, with temperature. Gases flow very freely. Gases have relatively low density. Gases are freely miscible with each other, and they form a solution in any proportions. Pressure is defined as force divided by area. Atmospheric pressure arises from the force exerted by atmospheric gases on the Earth's surface. Atmospheric pressure is usually 14.7 pounds per square inch. So a pressure of 14.7 pounds per inch, a square inch exists on the outside of your room or your body, and it equals the pressure on the inside. What would happen if the inside and the outside pressure on a container were not equal? In this diagram, we show a can with pressure outside equal to the pressure inside. The can maintains its shape. When this pump is turned on, the pump pulls gases away from the pan inside, and the pressure inside becomes smaller. The difference of the pressure outside and inside can easily crush the can as shown on the right side. Atmospheric pressure can be measured by a Mercury Barometer. A barometer can be made first by adding mercury into a tube about 1 meter long with one end sealed. The tube is then inverted into a dish with more mercury. When the tube is inverted, some of the mercury flows out into the dish, and a vacuum forms above the mercury remaining in the tube. At sea level, under ordinary atmospheric condition, the mercury stops flowing out when the surface of the mercury in the tube is about 760 milliliters above the surface of the mercury in the dish. At this height, the column of the mercury exerts the same pressure on the mercury surface in the dish as the atmosphere does. In other words, this height measures the atmospheric pressure. Atmospheric pressure is not always the same. For example, at the top of Mount Everest, the atmospheric pressure is only 270 millimeter mercury height, so atmospheric pressure decreases with altitude. You may have learned in physics that pressure due to a liquid is calculated by density times gravity times height. For 760 milliliter mercury height, the pressure can be calculated by density of mercury, which is 13.6 gram per liter times gravity times 760. Now, if we use water instead of mercury, okay, then the pressure will be 1 gram per liter, that's the density of water, times the same gravity times the new height. So these two should be equal if we measure the same atmospheric pressure. So gravity cancel, and you can see here, if density is small, height must be very large. Okay, the calculated height for water is 34 feet. That's very inconvenient, and that's why barometer is usually made by mercury for measuring atmospheric pressure. So in general, for a given pressure, the ratio of height of the liquid columns is inversely related to the ratio of the density of the liquids. In the last slide, we showed how barometer can be used to measure atmospheric pressure. Manometers are also commonly used to measure the pressure of a gas in an experiment. Here shows two types of manometers. In a closed-end manometer, a mercury-filled curved tube is closed at one end and attached to a flask at the other side. When the flask is evacuated, the mercury levels in the two arms are the same because no gas exerts pressure on either mercury surface. When a gas is in the flask, it pushes down the mercury level in the left arm and causing the level to rise in the right arm. The difference in column heights, the delta H, equals the gas pressure. In an open-end manometer, this side is not closed but open to the atmosphere. The atmosphere pushes on one mercury surface and the gas pushes on the other. The delta H is therefore the difference of the two pressures. Remember, in closed-end manometer, delta H equals the pressure of the gas. In this case, delta H is the difference. Now, because this atmosphere pushes down more than the gas on the right side, and therefore the pressure of the atmosphere is greater than the gas pressure. So the pressure of gas in this case is equal to the pressure of atmosphere minus delta H. In this diagram, because the gas pushes down more than atmosphere, and so the gas pressure is greater than atmosphere by delta H. So in this case, the pressure of gas should equals to the atmosphere pressure plus delta H. Pressure is defined as force divided by area. In SI unit, force is in Newton, area meter squared. So the SI unit for pressure should be Newton per meter squared. This unit is also called Pascal. So Pascal is equivalent to Newton per meter squared. The normal atmospheric pressure at sea level and 0 degree is called 1 atmosphere, which is 760 millimeter mercury height, which is equivalent to 1.01325 times 10 to the 5th power Pascal, or 101,325 kilopascal. Millimeter mercury height is also called torr. So 1 atmosphere is 760 torr, which is equivalent to 14.7 pounds per inch squared. 1 bar is exactly 10 to the 5th Pascal. So 1 atmosphere should be 1.01325 bar. Sample problem 5.1. A geochemist heats a limestone sample and collects the CO2 released in an evacuated flask attached to a closed-end manometer. After the system comes to room temperature, delta H is 291.4 mm mercury height. Calculate the CO2 pressure in torrs, atmospheres, and kilopascals. In a closed-end manometer, one end is sealed with vacuum, so delta H equals the pressure of the gas. In this case, is the CO2 pressure. So delta H, this one, is the CO2 pressure. Now, it given is in millimeter mercury height. It asks to convert to torrs, atmospheres, and kilopascal. So we need to refer to the last slide's table and using those numbers as conversion factors. We start with the given 291.4 mm mercury height. To convert the millimeter mercury height to torr, we look at the table millimeter mercury height and torr, and we find they are equivalent. So 1 torr equals 1 millimeter mercury height. So we write conversion factor 1 torr 1 millimeter mercury height, and that gives you 291.4 torr. To convert from torr to atmosphere, we look at the table 1 atmosphere equals 760 torr. So we write conversion factor 1 atmosphere 760 torr. So cancel torr, give you atmosphere. To convert from atmosphere to kilopascal, we look at the table 1 atmosphere equals 101.325 kilopascal. So we write a conversion factor 1 atmosphere is equivalent to 101.325 kilopascal. So cancel atmosphere, give you kilopascal. A gas is described by 4 variables: pressure, temperature, volume, and number of moles. These 4 variables are not independent, but related by mathematical equations called gas laws. An ideal gas is a gas that exhibits linear relationships among these variables. Although no ideal gas actually exists, but the most simple gases behave nearly ideally at ordinary temperatures and pressures. One of the gas laws is called Boyle's law. It is experimentally found that when temperature is kept constant, the volume occupied by a fixed amount of gas is inversely proportional to the external pressure. So volume, pressure are inversely proportional. Mathematically, we can write volume is proportional to the inverse of pressure, or pressure times volume is constant. Now, because volume and pressure are inversely proportional, so when one decreases, the other increases. So pressure increases, volume decreases. However, you must remember the condition for the Boyle's law is the temperature and number of moles are kept constant. This illustrates the setup that Boyle might have used in his experiment. A J-shaped glass tube with one end sealed. After mercury is poured into the long open leg, a small amount of gas is trapped in the other side. Initially, the volume of the trapped air is 20 mm, and the delta H is 20 mm mercury height. This delta H measures the difference of the pressure of the gas and the atmosphere. So the pressure of the gas should be the pressure of the atmosphere plus 20 millimeter mercury height. So 760 plus 20 give you 780 millimeter mercury height, or tall. Okay, so that's the beginning. And now, when more mercury is added, the added mercury will increase pressure and reduce the volume until the delta H becomes 800 millimeter mercury height. At this point, the pressure of the trapped air should be atmosphere plus 800. So 760 plus 800 give you 1560 torr. So the pressure change from 780 to 1560, that's increased twice. And the volume from 20 becomes 10. So increase volume or increase pressure twice, decrease volume to half of it. Okay, and if we plot this data, okay, this is a table, this is more data. All right, so initially the volume is 20, the pressure is 780. Okay, so that's this point. When increase pressure to 1560, the volume decrease to half of it. So that's this point. Okay, so increase volume of pressure, decrease volume. Pressure volume are inversely proportional. If we plot volume against the inverse pressure, we get a straight line. And that's exactly what we talked about in the last slide. Volume and the inverse pressure are proportional, or pressure volume inversely proportional. The product is a constant. Boyle's law is at a constant temperature. In Child's law, pressure is kept constant. It is experimentally determined that the volume occupied by a fixed amount of gas is directly proportional to its absolute temperature. So volume, temperature are proportional. Or we can write as volume divided by temperature is a constant. So if the ratio is constant, then when one increases, the other must also increase. When one decreases, the other must also decrease. And that's the Child's law. Pressure, number of moles are kept constant. Volume, temperature, they are proportional to each other. Here is a setup that can be used to confirm Child's law. A water bath with a thermometer to measure temperature, a straight glass tube with a small amount of air trapped by a mercury plug. The pressure of this air is equal to the plug height plus the atmosphere. So let's say the plug is 5 millimeter and the pressure, atmosphere pressure is 760. And since neither of these pressures changes during the process, the pressure of this air is kept constant. Initially, some ice is added, so the temperature is maintained at 0 degrees, and the volume of this air is measured to be 0.8965 liter. Now a heater is added, so the temperature of the water bath gradually increases, and the volume of the air expands slowly. The higher the temperature, the more the volume expands. At 25 degrees, the volume increased to 0.9786. At 50 degrees, it goes to 1.061. Okay, when the temperature is converted to absolute temperature, Kelvin, and plot volume against absolute temperature, we get a straight line that goes through the 0 Kelvin. So volume here is proportional to absolute temperature times a constant. So C is a constant. Or we can say volume divided by temperature is a constant. If we change the amount of gas trapped in the system, all right, or if we change the pressure, so add more mercury, okay, then we redo the experiment, we'll get another straight line with a different slope. But in any event, volume is proportional to absolute temperature. And the volume divided by temperature is always a constant. And that's Child's law. Here shows a setup that can be used to confirm Child's law. A water bath with a thermometer to measure temperature, a straight glass tube with some air trapped by a mercury plug. The pressure of this air is equal to this mercury plug height plus the atmospheric pressure. So let's say the mercury plug is 5 millimeter and atmospheric pressure is 760 millimeter mercury height. Since neither of these changes during the process, the air pressure is kept constant. Initially, some ice is added, so the temperature is maintained at 0 Celsius or 273 Kelvin. And the volume of this air is measured to be 0.8965 liter. Now, a heater is added to heat the temperature, and the volume of the air starts to expand. The higher the temperature, the more the volume expands. At 25 Celsius, the volume becomes 0.9786. When temperature goes to 50, volume becomes 1.061. If we plot volume against temperature in Kelvin, absolute temperature, we get a straight line. In mathematics, a straight line is y equals kx. K is the slope. So in this case, volume is a constant slope times absolute temperature. So that's the slope. Let's say C1 for this straight line. Or we can write V divided by temperature is the slope. If we change the volume, if we add more gas, okay, trapped in this setup, or if we add more mercury, so the pressure increase. So at a different constant pressure, okay, and then we redo the experiment, replot it, we get a different slope. Okay, we get a straight line but with different slope. So volume equals C2 times T. V equals C3 times T. But in any event, volume temperature is proportional to each other. The curve, the plot is linear. All right, so volume divided by temperature is always a constant. In Boyle's law, temperature is kept constant. In Child's law, pressure is kept constant. When both temperature and pressure are kept constant, and we study the volume as a function of the amount or number of moles of the gas, we get Avogadro's law. Experimentally, we found that volume occupied by a gas is directly proportional to the number of moles, the amount of gas. Here is a setup we can demonstrate Avogadro's law. A test tube connects to a piston cylinder assembly exposed to atmosphere. In the first step setup, we add 0.1 moles of solid carbon dioxide or dry ice. In the second setup, we add twice the amount of carbon dioxide, dry ice, which is 0.2 moles. And when the temperature goes up, dry ice evaporates and becomes gas phase. And we found that in the second setup, the volume is twice as the volume in the first setup. So pressure is the same, temperature is the same, number of moles increase twice, volume increase twice. Volume, number of moles is proportional to each other. Avogadro's law says that at a fixed temperature and pressure, equal volume of any ideal gas contain equal number of particles or moles. Standard temperature and pressure, or STP, is defined as a condition when pressure is 1 atmosphere or 760 torr. Temperature is 0 Celsius or 273.15 Kelvin. At this condition, 1 mole ideal gas has a volume 22.4 liter, and this is called the standard molar volume. Here shows 3 different gases: helium, nitrogen, oxygen, at standard temperature and pressure, 0 Celsius, 1 atmosphere. Although they may have different density, different mass, as long as they have same number of moles, 1 mole, they occupy the same volume, 22.4, 22.4, 22.4. We have discussed the 3 individual laws. In Boyle's law, number of moles and temperature are kept constant. We found that volume is inversely proportional to pressure. Volume is constant divided by pressure, or pressure times volume is a constant. In Child's law, number of moles and pressure are fixed. Volume is proportional to temperature, so volume is a constant times temperature. In Avogadro's law, pressure and temperature are kept constant, and the volume is proportional to number of moles, so volume is constant times number of moles. If we combine all these individual laws together, we find the equation that left side is pressure times volume, and the right side is temperature, number of moles, so N times temperature times a constant. Okay, the constant we usually use R as a gas constant, so PV equals N times a constant R times T. So this equation connects all the 4 variables: pressure, volume, temperature, number of moles, and this is called the ideal gas law. In ideal gas law, PV equals nRT. R is a constant. To find the value of R, we modify this equation. So R should equals to the left side PV divided by N times temperature. Let's use standard temperature pressure. to calculate R. Standard temperature is 273 Kelvin. Pressure is 1 atmosphere. And we already know that under this condition, 1 mole of ideal gas occupies 22.414 liter. So plug in all the data, we calculate this equation, we get 0.0821 atmosphere liter per mole per Kelvin. And that's the R constant. Okay, note that the pressure is atmosphere and the volume is liter. Temperature always Kelvin, but the pressure volume may have different units. So if pressure volume have different units, the value of the R will change. And this is important to remember. So R equals 0.0821 only when pressure is in atmosphere and volume is in liter. Now since R equals PV divided by R and T, R is a constant. So at condition 1, we have P1 V1 divided by N1 T1. At the different condition, we have P2 V2 divided by N2 T2. But both are R, and therefore they are always equal. And this is called combined equation. Sample problem 5.2. Boyle's apprentice finds that the air trapped in a J tube occupies 24.8 cubic centimeter at 851 torr. By adding mercury to the tube, he increases the pressure of the trapped air to 2.64 atmosphere. Assuming constant temperature, what is the new volume of the air in liter? Here is the setup for the Boyle's experiment. And this is the straight glass tube with trapped air inside. Initially, the volume is 24.8. So this is the initial volume, V1. And pressure, here, pressure equals the atmosphere plus the mercury plug. So this added together, initially, that's P1. So P1 is 851 torr. Now, when you add more mercury, so when mercury is added, the pressure increase. Okay, so it increased to 2.64 atmosphere. So this is the P2. Okay, the pressure change from P1 to P2. The question is, what is the new volume V2? Okay, so we know that when we add mercury, increase pressure, the pressure volume will decrease. The question is, what is the volume, new volume? Now, according to the Boyle's law, pressure times volume is constant. So P1 V1 should equal to P2 V2. So P1 V1 are given, P2 is given, so V2 can be calculated. So V2 should be P1 V1 divided by P2. Okay, but first you notice that the unit given cubic centimeter and ask for liter. All right. Also, pressure given is torr, and P1 is in torr, P2 is in atmosphere. So the unit has to be consistent, and therefore the first step you need to convert units from torr to atmosphere, from cubic centimeter to liter, and then use this Boyle's law to calculate V2. First, let's convert 851 torr to atmosphere. So we start with torr. Okay, we use 1 atmosphere equals 760 torr as a conversion factor. So torr cancel, give you atmosphere. Next, we convert a cubic centimeter to liter. So cubic centimeter, and we first convert to milliliter. So 1 milliliter, 1 cubic centimeter. So now we have a milliliter, and then 1 liter, 1000 milliliter. So cancel milliliter, give you liter. All right, so now the units are consistent. We use this equation, the Boyle's law, we calculate V2. So plug in everything here, and you get 0.0105 liter. Sample problem 5.3. A balloon is filled with 1.95 liter of air at 25 degrees and then placed in a car in the sun. What is the volume of the balloon when the temperature in the car reaches 90 degrees? Well, the volume of balloon can change, but the pressure is constant because the pressure of the gas inside the balloon equals the pressure outside, which is the atmospheric pressure. So this is about constant pressure, and number of moles inside the balloon is also constant. And that tells you this is about Child's law. So Child's law is when pressure, number of moles are kept constant. Volume is proportional to temperature. So constant times temperature. Or we can write volume divided by temperature is constant. Or we can write V1 T1 divided by V2 T2. So in this case, we have this is the volume V1, and temperature is T1, and then you place in car, so temperature goes up. So when temperature goes up, and this becomes T2, and the question is, what is the new volume? That's V2. So we have V1, T1, T2, and we want to calculate T2. Okay, so using this equation, modify this equation, we can calculate V2. But first, are the units consistent? So here, temperature, Celsius, must be converted to Kelvin. Okay, whenever we use gas laws, temperature must be converted to the Kelvin. All right, and volume, if V1 is little, then V2 will also be the same. Okay, now if you don't remember the Child's law, we can always use the ideal gas law and the combined law, gas law. So ideal gas law says R constant equals PV divided by NT. Okay, because PV equals nRT, so R equals PV divided by NT. So for condition 1 is P1 V1 N1 T1. For condition 2 is P2 V2 N2 T2. Okay, now in this case pressure constant, so you cancel pressure. The number of moles kept constant, and so that gives you this Child's law. Okay, so first we convert temperature to Kelvin. All right, so these are given, volume V1, all right, and we want to calculate V2. Okay, and T1 are Celsius. To convert to Kelvin, we add 273, you get the T1, T2, and then use the Child's law. Okay, again, if you don't remember, you can use combined law and derive the Child's law, and then you can calculate the V2. Okay, plug in everything, and the answer is 2.38 liter. Sample problem 5.4. A scale model of a blimp rises when it is filled with helium to a volume of 55 cubic decimeter. When 1.1 moles of helium is added, the volume is 26.2 cubic decimeter. How many more grams of helium must be added to make it rise? Assume temperature, pressure are constant. When temperature, pressure are constant, gas obeys Avogadro's principle, and that is volume is proportional to number of moles times a constant. Okay, or volume divided by number of moles is a constant, or volume 1 N1 equals volume 2 N2. Okay, so in this case, we have volume 1, and so this is volume 1. We have okay, actually this is volume 2. This is what we want to make. And here, this is volume 1. Okay, this is N1. Okay, so when number of moles is 1.1, volume is 26.2. And we want to calculate N2 to make volume 55. Okay, so using this equation, we should be able to calculate N2. Now, units are consistent. And also, what if we don't remember Avogadro's principle? We'll always use gas laws. So combine the gas laws as ideal gas law, PV equals nRT. So R should equals to PV divided by nRT, so NT. And for condition 1, P1, V1, N1, T1. Condition 2, P2, V2, N2, T2. Okay, so in this case, temperature is constant. So this is constant, and the pressure constant, and that gives you V1 divided by N1 equals V2 divided by N2. Okay, and so in this case, temperature, pressure constant, we use Avogadro's principle, and these are given, and modify the equation, we can calculate N2. All right, so N2 equals N1 times V2 divided by V1. Plug in all the data, give you 2.31 moles of helium. So that's what you need to make it rise. Now, initially, you already have 1.1. So the additional amount should be 1.2 or 1.21 moles of helium. So use final minus initial. Okay, and it asks you grams. So to calculate grams, you use moles times molar mass. For helium is 4.003 gram. So that gives you 4.84 grams of helium should be added. Sample problem 5.5. A helium-filled balloon has a volume of 15.8 liter at a pressure of 0.98 atmosphere and 22 Celsius. What is its volume at summit of Mount Hood, Oregon's highest mountain, where the atmospheric pressure is 532 millimeter mercury height and temperature is 0 Celsius? So we have volume 1 of the balloon, and the pressure P1, okay, and the temperature T1. All right, note that this Celsius needs to be Kelvin. And then we at a different elevation, so high elevation, the pressure goes to this one, that's P2. And temperature is 0, so that's T2. Again, this goes to Kelvin. The question is, what is volume, which is V2? Okay, so we have two different states of the same gas, and we should use the combined gas law. R equals PV and T. So P1, V1, N1, T1 equals P2, V2, N2, T2. Because the number of moles is fixed inside the balloon, so N cancel. So we have P1, V1, T1, and these are all given right here, the state 1. In state 2, at high elevation, we have P2, V2, okay, oh, sorry, T2. We want to calculate T2, V2. Okay, so we have everything else except V2. We can calculate V2. But first, we need to convert the temperature from Celsius to Kelvin. All right, and also note that the pressure P1 is atmosphere, and P2 is millimeter mercury height. And so we need to convert the unit to be consistent. So either atmosphere to mercury height, millimeter mercury height, or we can convert the millimeter mercury height to atmosphere. Here are the given conditions. State 1, V1, T1, P1. State 2, T2, P2, constant number of moles. We want to calculate V2. Okay, so first let's convert temperature from Celsius to Kelvin. We add 273. Okay, so we get T1 and T2. Now let's convert pressure from millimeter mercury height to atmosphere. Okay, so we use 532 millimeter mercury height divided by 760 millimeter mercury height, which is equivalent to 1 atmosphere. So cancel millimeter mercury height, give you atmosphere. So that's P2. All right. So now the combined gas law, number of moles are the same. So we have this one and modify it to calculate V2. We have V1 times P1 T1 divided by P2 T1. P1 T2 divided by P2 T1, which is so everything plug in the data, and the answer should be 20.5 liter. Sample problem 5.6. A steel tank has a volume 438 liter and is filled with 0.885 kilogram of oxygen. Calculate the pressure of oxygen at 21 Celsius. Okay, so this question tells you the volume, the temperature, so volume, temperature. All right, now it asks you calculate the pressure. It doesn't tell you the change as we did in the last few problems. Those problems involve change from pressure P1 to P2 or T1 to T2 or V1 to V2. So if you see those state change, that indicates that we need a combined gas law. Let's say P, V, and T. So P1, V1, T1, N1, T1 equals P2, V2, N2, T2. So that's the combined gas law for the state change. But for this case, it's a steel tank. Volume is constant. It doesn't change. Temperature doesn't change, and the pressure doesn't change. It asks you the pressure, and therefore this type of question you need the ideal gas law. PV equals nRT. So temperature first change to Kelvin. So temperature is given here, and volume is given. All right, here, and it asks you the pressure. To use this equation to calculate the pressure, we also need to know the number of moles. The given also give you kilogram. So kilogram needs to change to moles. Okay, and so with number of moles, then we can use this ideal gas law to calculate the pressure. Okay, so first we change temperature to Kelvin. Okay, and then we convert kilogram to grams and then to moles. So we start with kilogram, we change to grams, so times 1000, all right, 1000 gram equals 1 kilogram. Now we have grams, and then divided by molar mass. So 1 mole oxygen, 32 grams of oxygen, and that changed to moles. Now we plug in everything into this equation. So this equation modify, you can calculate the pressure, nRT divided by volume. Okay, so in this equation, we still need to know the R constant. Since the unit for volume is in liter, and pressure will give you atmosphere, and the R we can use 0.0821. Okay, so this is the value for R when the volume is in liter and the pressure in atmosphere. Okay, so plugging everything and the calculated answer is 1.53 atmosphere. Sample problem 5.7. The piston cylinder is depicted before and after gas reaction that is carried out under constant pressure. The temperature is 150 Kelvin before the reaction, 300 Kelvin after the reaction. Which of following balanced equation describe the reaction? Now, before we look at the chemical reaction, let's first look at the system change. It is under constant pressure, so pressure are the same. Okay, according to Boyle, the Child's law, if pressure, number of moles kept constant, volume will be proportional to the temperature. So constant times temperature. So increase temperature, increase volume. So in this case, temperature increased twice from 150 to 300 Kelvin. Volume should also increase twice. But if we look at the diagram, volume is the same. So what keep the volume constant? Okay, what keep volume the same? It must be due to the chemical reaction. So the reaction, after the reaction, the number of moles must reduce to half of it. Because if pressure, number of moles both are kept constant, then increased temperature must increase volume. That's the Child's law. Okay, so here we are looking at a chemical reaction that reduces the number of moles. So after the reaction, the number of moles must be half of the number of moles before the reaction. Okay, so let's look at each of them. In A, reactants 1 mole A, 1 mole B forms 2 moles AB. So 1 plus 1, 2. Before reaction 2, after reaction 2. So the number of moles doesn't change. So this is not our choice. Number 2, 2 moles AB, 1 moles B. So that's 3 moles reactants. And products is 2. So that's not our choice because the number of moles doesn't reduce half of it. Okay, in 3, 1 moles A, 1 mole B forms 1 mole AB2. So 2 moles reactants forms 1 mole product, and that is our choice. Okay, that's the correct answer because the number of moles reduce half of it. And if you look at 4, 2 moles AB2, so that's reactants. And product is 1 plus 2 is 3. So 2 goes to 3. That's not our answer. Okay, so the answer should be 3. These slides give you more explanation of sample problem 5.7, and the answer is 3. A plus B2 goes to AB2. The number of moles reduced to half of it.